when you're ready.
Thank you. Hello everyone, I'm Yucen from Shanghai Jiaotong University. Today I want to share our paper titled a Dual-Embedding-based DQN for worker recruitment in spatial crowdsourcing with social network. I will break it down into 5 parts. Let's start with the background. In this paper, we focus on the problem of worker recruitment for spatial crowdsourcing. Spatial crowdsourcing is a very common service in recent years, which requires workers to arrive at a designated place to complete the task in order to receive rewards. Common applications include Didi, Uber Eats, and so on. Worker recruitment is a core problem in spatial crowdsourcing. Most of the current advanced methods aim to design worker-inductive mechanisms to make workers in the existing worker pool participate in the tasks. However, if the number of workers in the existing worker pool is insufficient, these methods may fail, especially for some new platforms. In recent years, several studies have found that social networks are beneficial for worker recruitment tasks. As shown in the figure, we can expand the existing worker pool by selecting some people in the existing working pool as seed workers, so that they can pass the task information on the social network to simulate more people to participate in the crowdsourcing tasks. However, because we need to pay the seed workers for additional information propagation, we would like to select as few seed workers as possible to achieve higher task completion quantity. Therefore, how to select the appropriate seed workers is still a challenging problem. To solve this problem, we first give a normalized definition of the problem. We first define the social network and the task propagation model so as to obtain the probability formula of node activation. We then define the notion of effective coverage. Because in realistic scenarios, there is an upper limit to the task demand. We take minimal C divide D and 1 as the effective coverage. Based on the above definition, we give a complete definition of the effective coverage maximization problem. That is, given the social network G, the existing worker pool P, and the ability of each worker, the goal of our problem is to select at most K seed workers such that the effective coverage is maximized. Here we do some discussions. Firstly, the ECM problem is not equivalent to the traditional influence maximization problem, because the goal of the influence maximization problem is to maximize the number of influenced nodes. However, the existing methods for solving the influence maximization problem are difficult to achieve good results when transferred to our ECM problem, because these methods rely on multiple iterative searches, which will lead to low efficiency. So how to solve the ECM problem with high quality and efficiency? We try 3 aspects, namely characterizing the social influence of nodes, characterizing the task completion ability of nodes, and using reinforcement learning method to improve the performance and efficiency simultaneously. Here is our framework diagram of our model, DQN selector. For social networks, we use Monte Carlo simulation and stochastic gradient descent to estimate the social influence of nodes. For geographic information graphs, we design a hierarchic tree-based PIC algorithm to estimate the task completion ability of nodes within the range of R-hoops. Based on these 2 embeddings, we use rainbow DQN to obtain the final site of our seed workers. Specifically, For the learning of social influence, we consider both the influencing ability and the influenced ability of a node, which are denoted by S and T, respectively. We use Monte Carlo simulation to find the influence of V on U, and then use stochastic gradient descent to find the node embedding SV and TU. For the task completion ability within R hops of a node, we designed the PRIC algorithm. The algorithm is designed based on the hierarchic tree of information propagation. That is, the information propagation of L layers depends on the sum of the information propagation of L-1 layers, which means that the results of the previous layer can be used to quickly obtain the results of the next layer, so as to accelerate the calculation. We incorporate these two embedding vectors into the state design of DQN. On the right side of this slide is the training process of our rainbow DQN, which I will not introduce in detail here. Next, let's look at the situation of the experiment. This site we used is the open source real-world dataset Swallow and Brightcage, and the table shows some of their statistical properties. Baseline methods we used are 6 methods, including greedy algorithms, heuristic algorithms, and the reinforcement learning method. In terms of performance, the chief algorithm will achieve the better results, but because it needs to calculate the marginal effect of all the remaining nodes in each step, so its solution speed is very slow, as shown in Table 2. However, our DQN selection method achieves the second best performance because it considers both influence and multi-step task completion ability. In terms of solution time, DQN selector is only slower than greedy, but its performance is much higher than the greedy. Therefore, we believe that DQN selector is a method that strikes a balance between solution performance and time. At the same time, we also do ablation experiments to verify the effectiveness of our Purpose 3 components. We make a summary of our paper contribution here. That's all. Thanks for listening.